Good morning. Welcome to our distinguished visitors, members of the press, NSF staff, and National Science Board members represented by Dr. Maria Zuber of MIT. Scientists from the LIGO, Virgo, and GEO scientific collaborations, members of the Caltech and MIT communities, and all our guests. I specifically want to recognize representatives from the Max Planck Society, the UK Science and Technology Facilities Council, and the Australian Research Council, whose generous contributions have also helped bring us to today. I'm Dr. France Cordova, the Director of the National Science Foundation. Without a doubt, the reason so many of us are here today is because we believe in the potential of the Laser Interferometer Gravitational Wave Observatory. Opening a new observational window would allow us to see our universe and some of the most violent phenomena within it in an entirely new way. Since the mid-1970s, the National Science Foundation has been funding the science that ultimately led to LIGO's construction. And in 1992, when then NSF Director Walter Massey and the National Science Board approved LIGO's initial funding, it was the largest investment NSF had ever made. It was a big risk, but the National Science Foundation is the agency that takes these kinds of risks. We support fundamental science and engineering at a point along the road to discovery where that path is anything but clear. NSF funds trailblazers. It's why the U.S. continues to be a global leader in advancing knowledge. So, without further delay, because I too am eager to hear the latest updates from LIGO's lead scientists, let's kick things off with a video and then go to Dave Reitze, who is LIGO's executive director.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
The gravitational wave stretches space in one direction and compresses space in the other direction.
Nobody really believed that you could ever detect them because the size of the effect is so small.
I came to the conclusion that, yeah, if you made this long enough.
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
That's what scientific discovery is really all about. You don't choose the simple things to do.
We have done something which is brand new.
The field is busted wide open.
It's monumental. It's like Galileo using the telescope for the first time.
I looked at it and I thought, my God, this looks like it's it.
Ladies and gentlemen, we have detected gravitational waves. We did it. I am so pleased to be able to tell you that. So these gravitational waves were produced by two colliding black holes that came together, merged to form a single black hole about 1.3 billion years ago. They were detected by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is the most precise measuring device ever built. Let me start with what we saw. So on September 14th, 2015, the two LIGO observatories in Hanford, Washington, and Livingston, Louisiana, recorded a signal nearly at the same time, nearly simultaneously, and the signal had a very specific characteristic. The characteristic of, as time went forward, the frequency went up. And what was amazing about this signal is that it's exactly what you would expect, what Einstein's theory of general relativity would predict for two big massive objects like black holes in spiraling and merging together. Now, it took us months of careful checking, rechecking, analysis, looking at every piece of data to make sure that what we saw was not something that wasn't a gravitational wave, but in fact it was a gravitational wave. And we've convinced ourselves that's the case, and we're here to announce that today. But I do want to say something else. This is not just about the detection of gravitational waves. That's the story today. But what's really exciting is what comes next. Right? It's 400 years ago, Galileo turned a telescope to the sky and opened the era of modern observational astronomy. I think we're doing something equally important here today. I think we're opening a window on the universe, the window of gravitational wave astronomy. So I'm going to show you two videos that are going to sort of tell you what we discovered. So the first video is the two black holes. So what you're looking at on the screen here are two black holes. Each of them are about 30 solar mass, have about 30 times the mass of the sun. All right, and you're looking, the black holes are the black things in the middle, and you're looking at the stars behind them. By the way, this is not a Hollywood production that I'm going to show you. It is actually a real computer simulation solving Einstein's equations for these merging black holes. So this is really what it would look like if you were in a spaceship close up. And I will also point out that the movie I'm showing is vastly slowed down relative to what happened here. So let me start it. All right, you can see that as the black holes spin around each other, all right, the stars behind them are warped, and that's because the strong gravitational fields bend the light that comes around. But what I want you to pay attention to in this video is the fact that as they orbit, the black holes are getting closer and closer to one another. The orbit is speeding up, and eventually they're going to merge. The event horizons are going to join, boom. They produce one big black hole, which relaxes, and you see a little bit of vibration there, and it becomes two smaller black holes die, one bigger black hole is born. Now, what's really amazing about this is the first time that this kind of a system has ever been seen, a binary black hole merger, and it's proof that binary black holes exist in the universe. So I want to put this in perspective for you because I think it's very important, all right, to give a sense of what really happened here. So each of these black holes are about 150 kilometers in diameter, a little bit bigger than that. Take something that's 150 kilometers in diameter, so that's about a little bit bigger, maybe a lot bigger than the metropolitan Washington, D.C. area. Pack 30 times the mass of the sun in that. Accelerate it to about half the speed of light. Now take another thing, 30 times the mass of the sun. Accelerate at half the speed of light and collide them together. That's what we saw here. It's mind-boggling. All right, now, let me talk about the gravitational waves. You didn't see any gravitational waves there. What you saw was actually the black holes. Now let me look at this from the gravitational wave perspective. So you're going to see, again, a computer simulation. This is a real simulation using Einstein's equations. You see the two black holes. And the green that you see are the gravitational waves that are produced as the black holes orbit around one another. Their orbit decays and they merge together. All right. So they're spinning around. You see they're getting closer and closer together. As they get closer and closer together, more gravitational waves, they merge, and there's this burst of gravitational waves that travels for 1.3 billion years. It passes through everything. It goes right through matter, right through stars, and it eventually gets to the Earth. All right, and when it gets to the Earth, the gravitational wave passes, and what it's going to do is stretch and compress space as these waves pass. And you'll see that the Earth is jiggling like jello. I don't want people to be scared here. The Earth doesn't really do this. This effect is greatly, greatly exaggerated, but it gives you the effect. And then we zoom in, and how we detect these are using the interferometer that's in LIGO. And Ray Weiss is going to tell you more about the interferometer. I just want to say one thing. that the effect that we're trying to measure from these violent, these big black holes colliding each other at half the speed of light, all right, is so tiny that it takes something like LIGO to measure it. We are trying to measure things basically at 1/1000th the diameter of a proton. That's the size of the signal that you see on Earth from those events that take place 1.3 billion years away. All right. Let me put that in perspective because I think those kinds of numbers are hard to get your head around. All right. If we were trying to measure the distance between the sun and the nearest star, which is about 3¼ light years away, LIGO is capable of measuring that, if it could do that, to a level of about the width of a human hair. So the width of a human hair over 3¼ light years. That's remarkable precision. Right? Now what LIGO does is it actually takes these vibrations in space-time, these ripples in space-time, and it records them on a photodetector, and you can actually hear them. So what LIGO has done, it's the first time the universe has spoken to us through gravitational waves. And this is remarkable. Up till now we've been deaf to gravitational waves, but today we're able to hear them. That's just amazing to me. I think this is big, again, because what's going to come now is we're going to be able to hear more of these things. And no doubt we'll hear things that we expected to hear, like binary black holes or perhaps binary neutron stars colliding. But we will also hear things that we never expected. And as we open a new window of astronomy, we may see things that we never saw before. So let me conclude by thanking the National Science Foundation. For 40 years, since the NSF started funding Caltech and MIT to do pilot experiments for LIGO, and then in 1992, the NSF went ahead and funded the LIGO project, right? And they took a big risk. All right, this was bold. The science was solid, but we didn't know how many events we would see. The technology was nowhere near developed. This was truly, I think, a scientific moonshot. I really believe that. And we did it. We landed on the moon. So I really want to thank Dr. Cordova and NSF, and also U.S. Congress, taxpayers who supported this research, because it's really gotten to the point now where it's going to take off. So I'm going to conclude my remarks, and I'm going to introduce my esteemed colleague, Gabby Gonzalez. Gabby is a professor of Louisiana State University. She's also the spokesperson for the LIGO Scientific Collaboration, and she's going to tell you more about this event and about the team that discovered it and about the observatory. So I turn it over to Gabby.
Thank you. It's an honor to be here to tell you about this fantastic discovery. This discovery has taken a long time. This has been a long journey, but it also has been the work of many people. There's only a few of us here, but there are now more than 1,000 people working on this, and there have been hundreds of people developing the technology, doing the analysis, and building these detectors. We are very proud of this work taking a village, a worldwide village. That was the LIGO Scientific Collaboration working together with the Virgo collaboration in Europe. And we have been analyzing data from 2 detectors in Hanford, Washington, and Livingston, Louisiana. LIGO built 2 detectors because we are measuring these tiny distortions of space-time here on Earth that you can only believe they're real if you see them both at the same time on places that are far apart. That's the only way to be sure that these are not local disturbances and they are coming from astrophysical sources. These detectors are L-shaped. This is the LIGO Livingston detector. They are 4 kilometers long on each side. That's a Hanford detector. And we have lasers that go back and forth between mirrors to measure the distance between those mirrors. And gravitational waves would distort the space-time and would be measured as distortions in that distance of 4 kilometers. Again, it takes a lot of people to do this, and you can see a lot of people, young people, doing this, as well as people who have been working on this for decades. So this is it. This is what we saw. September 14 last year, we saw this signal in Livingston, Louisiana. That is a measure, that's a waveform that we saw. The units are strain, that's a distortion of space-time, and you can see a peak value. The largest value of this waveform was a part in 10 to the 21. For 4 kilometers, that's a tiny, tiny fraction of a proton diameter. That's incredibly tiny. But this signal is seen, you can see it even by eye, above the ever-present rumbling noise that we have in the detector. But we know it's real because 7 milliseconds later, we saw the same thing in the Hanford detector. This is it. That's how we know we have gravitational waves. But we know a lot more than that. You can see that these signals have oscillations that grow in frequency and amplitude and then settle down. And that's exactly the prediction that we know from solving Einstein's equations on computers for the coalescence of two black holes, merging into a larger black hole and settling down. And the coincidence is remarkable. You can see here overlaid the template that we used or the numerical relativity simulation that was done for the coalescence of these black holes. That's how we know not only that we detected gravitational waves, but these waves were produced by the coalescence of black holes. So these are the fantastic news we are telling you about. Now, from these waveforms, you can tell a lot more. You can tell from the frequency the masses of the initial black holes. They had 29 and 36 solar masses. From the fitting to the numerical relativity waveform, we can tell that when they merged, they formed a larger black hole, but not with the sum of the two masses, with only 62 solar masses. And that's because there were 3 solar masses emitted in energy in gravitational waves. That's a huge amount of energy. And we can tell all of that from this tiny fraction of a second in the waveform. We can even tell more than that. From the amplitude of the waveform, you can tell how far away this system was. It was more than 1 billion light years away. This merger happened 1.3 billion years ago, when multicellular life here on Earth was just beginning to spread. And the signal took 1 billion years to come to Earth and produce this tiny distortion in our detectors that we are very proud to measure. Now, you can read a lot more details about these things in a paper that has just appeared online, peer-reviewed in Physical Review Letters. We are also publishing a lot more details in other papers that will be made public. Now, we can also put these waveforms, we can make a color plot time frequency diagram, and you can see the color denoting the amplitude, so it gets brighter as time goes on, and then dimmer when the black hole rings down. You can also see that the frequency is increasing. And the frequencies of these waveforms are in the human hearing range. We can hear gravitational waves. We can hear the universe. That's one of the beautiful things about this. We are not only going to be seeing the universe, we are going to be listening to it. Now, I wanted to play the gravitational wave for you to hear, but it's so short that it's just a thump. So what we have done is taken the real signal and shifted a bit in frequency, but it's still the real signal. Did you hear the chirp? There's a rumbling noise, and then there's a chirp. Let me do that again. That's the chirp we've been looking for. This is the signal we have measured. We can even tell more. Because we have 2 detectors, it's like having 2 ears, we can localize the signal. Not very well with only 2 years, but we can tell it came from the southern sky in the rough direction of the Magellanic Cloud, and we could have a broad area, a broad uncertainty area for the region. Of course, the source is a very point-like source. I mean, the merger happened in a small region, but we cannot tell exactly where it happened because we only had 2 detectors. But this will get better. We will have a network of gravitational wave detectors. GEO 600 has been working for decades as a technology demonstrator, but Virgo is going to come with a sensitivity closer to the LIGO detectors later this year. So we will have 3 years to localize the signals. And later on, we hope to include in the network the Kagra detector in Japan, and hopefully one in LIGO, India, very soon. So this is just the beginning. We discovered gravitational waves from the merger of black holes. It's been a very long road, but this is just the beginning. This is the first of many to come. Now that we have detectors able to detect these systems, now that we know that binary black holes are out there, we'll begin listening to the universe. Thank you. We'll hear now from Ray Weiss, one of the founders of LIGO, who will tell us about the history and the technology in these amazing detectors. Thank you.
Well, I'm going to tell you a little about history and then some about the instrument. And I want to first remind you of Einstein's 1915 big discovery, which was celebrated just recently, was really the formulation of these field equations, which were a completely different way to look at gravity. I mean, most of us were taught Newton. We talked about forces in gravity. Einstein didn't have that conception. He had the conception that actually space gets distorted. And you can see this in this picture of a membrane that is sitting under the sun, which is that yellow object, and then you can see a little dimple that's made by the Earth. And what that distortion in space and time is the thing that also tells those objects how they're supposed to move. So it's a completely different and a radical different idea about how gravity operates. And then in 1916, he applied these field equations to the idea of gravitational waves. There had to be something that communicated information, and it couldn't go faster than the velocity of light. That was already known. So what he then found is that there were waves in this theory that moved and propagated the velocity of light, and what they were strains in space. And I'll show you a strain in space, that's so you can visualize it. Here is this thing that, I don't know, I hope you can see. It's not the easiest thing. I'm going to make believe the gravitational wave that you're being demonstrated is coming at you. And I'll be the agency that moves the universe here. And you'll notice an interesting thing about it. If you look at any pair of points on this thing, what is a strain? A strain is the difference in distance that 2 points have as a function of time divided by their initial separation. And you'll notice that in the middle of this thing, it's small. That strain. The strain is the same all over this, but the amount of motion is small in the middle. It's quite large at the edges. And that's one of the reasons now you have some image why we had to build LIGO to be so big. You have to overcome a lot of other things that were going on. So we wanted to make sure that we made it long enough so you could see this. Now, even with this wonderful, enormous source that you've just heard about, and you know the numbers, the Einstein, first of all, could never have conceived of that. But even, let's just look at it. What it is that in the early days of, let's say, 1916, Einstein probably looked very hard at doing things himself. He was a practical physicist. He was a patent clerk. And what he probably did is he saw that these waves were generated by accelerating mass. And he probably put on the backs of envelopes, and we're looking for those envelopes. People don't have them, but they had to exist. Some calculations. Could you move a mass that's big enough? Could you measure it with the existing devices that existed in 1916? And you couldn't. Einstein was very despondent about that. He also then looked at astronomical systems like binary stars, and the ones he knew about in those days had long periods, and they just would never change aspect. Nothing would change about them as they were radiating gravitational waves. It was just too small. And so what's happened since then is two things have happened. One is that astronomers have found compact objects like black holes and neutron stars, which change the whole aspect of how fast things can accelerate. And then the other thing that really has changed is the technology. And that is an enormous step in the last 100 years. So with that, you're still now having these things, and I'll describe how we do this in a minute. Let me get you a little perspective. You've already had some, but I want a different perspective on what 10 to the minus 21 means. Okay? 10 to the minus 21 strain, everybody's saying, is 1,000th the size of a nucleus. So let's get to a little visceral feeling about that. I mean, the strain is 10 to the minus 21. If you now multiply that by 4 kilometers, you wind up with 10 to the minus 18. 10 to the minus 18 meters if you use, okay. Now, what is that? And most people don't know the 10 to the minuses, so they like to have it as, it's a decimal point, and 17 zeros, and then a 1. Okay, that's so, if you have to think of it as a fraction. And now let's look what that is. Start with a meter, and divide it by a million 3 times over. First time you divide it, you get a micron. So 10 to the minus 6. That's sort of the size of a cell, or maybe the 1,000th of your hair. Well, you've got much more to go. Then you divide by another million. And now you're at 10 to the minus 12. That's about 1/100th the size of an atom. And you're still not there. And now you divide again by another million, and you get to this number that we have to measure. And that's the 1,000th the size of a nucleus. So how do we do it? Well, we do it by timing light. That's how we do it. And I'll show you this in this. Here's a Michelson interferometer, which is the device that does the measurement. And what you'll see this round cylinder there, that's a laser. It's a make-believe laser. Then there's a beam splitter, which is that thing, which is a thin little thing in the middle. Then there are 2 mirrors, which have those black aspects, one to the left, one to the right. And then a make-believe detector, which is that rectangular thing. And now let me turn this animation on, and what we do is we fire light from the laser into the system. Now this is the electric field in the light. The color is the intensity of the light. So you'll see where the color tells you where the light is. But the electric field is indexed by the different colors of the field. And you'll notice the way this was set up is that right now there is no light at the photodetector. That's the trap you've set for the gravitational wave. And now people begin to wiggle in the animation, the end mirrors. And you'll notice light appears, disappears at the photodetector. That tiny motion and that fact, that light, the amount of light that goes to the photodetector is proportional to that strain in the gravitational wave. That's the method of the detection. Okay, now you're not done yet. You've got a device that measures tiny motions or tiny differences in time. But you're not done because you see those mirrors are sitting on the Earth, and the Earth is very noisy. It jiggles everything. And you want to make sure that the thing that jiggles the mirrors is only the gravitational wave. So we use all sorts of tricks. And I'll show you one of the tricks. Here's one of the tricks. What we do is we suspend the mirrors from a pendulum. Here's a sort of demonstration pendulum. And here's the mirror. And my hand will be the ground motion. And you notice if I move it very slowly or at low frequencies, the pendulum follows me. It follows the ground motion completely. Now let me wiggle it fast. And you'll notice the pendulum stands still while I'm wiggling. That's the basis of the idea. Now that's done with a tremendous elegance and, with cunning in this picture. This is what's actually in the apparatus. You see it on the screen now. And that is now 4 of these things in series. Okay? And by the way, the principle I just showed you is very much like the principle in a car. It makes you comfortable in a Cadillac and sort of bumpy in a truck. Yeah? Okay. Now, the thing is you're not done yet because there are other forces you have to worry about. And they are thermal noise, there's all sorts of noise, even quantum noise in this system. And all of that technology which has been developed, had it been available to Einstein in 2016, I would have bet that he would have invented LIGO. And he was smart enough, and he knew enough physics. He wasn't just a theorist. Okay? All right, now I'd like to introduce to you Kip Thorne, who is both a theorist and really an experimenter. And he was a visionary in this field because he thought about this many years, thought about all the sources, thought about what the theory really meant. And I want to give you a nice example from Kip's life. He wrote a book, a popular book that many of us have read. It's called Black Holes and Time Warps. And it says the undertitle is Einstein's Outrageous Legacy. And in that book, he tries to introduce the public to all those wild things that go on in the theory. And he has a group of people on a spaceship commanded by a woman who are going to visit all different kinds of black holes. The first place they go to is a stationary black hole. And that is like the one in our own galaxy. Then they go to a spinning black hole, and they look at that for a while. But then, very carefully, they approach a pair of black holes weighing 24 solar masses that are going around each other. And they merge into a single black hole. And then the universe gives a little burp when that is over. That's all in that book written, well, a chapter of that book was written in 1983. Okay? And we actually have seen it. So, Kip.
Don't forget your choice, Ray.
Ray is a modest man, but you should know that he was the primary inventor of the interferometers that detected these gravitational waves. And major additional contributions in terms of ideas came from Ronald Drever, who is the third founder of LIGO along with Ray and me. Unfortunately, Ron is too ill to be able to be with us today, but his family and he send their greetings. LIGO has been a half-century quest. It arose in part in the 1960s from pioneering work by Joseph Weber at the University of Maryland. And it arose from interferometer R&D in the 1970s and 80s at Caltech, MIT, in Scotland, and in Germany. In the late 1990s, Caltech and MIT built facilities for LIGO with funding from the National Science Foundation. And then in the late 1990s, LIGO was expanded to include scientists from many universities around the world and many nations, as Gabby Gonzalez described to you. In the 2000s, the initial interferometers were built and operated in LIGO as precursors to the advanced interferometers that we are telling you about today. The advanced interferometers were installed in between 2010 and 2015. They carried out their first gravitational wave search beginning last autumn with spectacular results almost immediately. Now, until now, we have only seen warped space-time. We as scientists have only seen warped space-time when it is very calm. It's as though we had only seen the surface of the ocean on a very calm day when it's quite glassy. We had never seen the ocean in a storm, roiled in a storm with crashing waves. All of that changed on September 14. The colliding black holes that produce these gravitational waves created a violent storm in the fabric of space and time. A storm in which time speeded up, then slowed down, speeded up again. A storm in which the shape of space was bent in this way and that way. We have been able to deduce the full details of the storm by comparing the gravitational waveforms that LIGO saw with the waveforms that are predicted by supercomputer simulations. And so here I'm going to show you a video that describes at the very bottom, it's not very bright, but at the very bottom is the gravitational waveform that was seen, cleaned of all of its noise. And it agrees beautifully with the gravitational waveform predicted by the simulations. And by seeing which simulation agrees in gravitational waveform, we can then go in and look at the computer simulation and deduce what I show you for the storm in the middle of the screen. And time is shown in the upper left of the screen, the flow of time. Now, the shape of space I show to you by imagining that we are living in a higher dimensional universe looking in on our universe. I take away one of the 3 dimensions from our universe so it looks like a surface, a 2-dimensional surface. And the flow of time, and then I should say that the funnels that you see in there represent the warping of space around the black hole. The flow of time is represented by the colors. In the green region near the center, time is flowing at its normal rate. In the yellow regions, it's slowed by 20 to 30%, and in the red regions, it's tremendously slowed. The silver arrows describe the motion of space. It's dragged into motion by the spins and the gravity and the movement, the orbital movement of the black holes, and then the motion of space causes the orbit to precess, as you saw. I'm pausing the movie now to watch the onset of the collision. You're going to see in slow motion the growth of the warping. I'm going to pause it, stop it here for a moment, and you can see the extreme warping, and then we see it oscillate and settle down finally into a single black hole. A new black hole has been born. Far away, in purple and blue, we see the gravitational waves propagating toward Earth, carrying the news of the collision. Now, the storm was brief, 20 milliseconds, very brief, but very powerful. The total power output in the gravitational waves during the brief collision was 50 times greater than all of the power put out by all of the stars in the universe put together. It's unbelievable, 50 times the power of all the stars in the universe put together. Because it was so brief, the total energy was not that big. It was only what you would get by taking 3 suns, annihilating them, and putting them into gravitational waves. Well, that's kind of a lot. And so, colliding black holes are not the only source of gravitational waves that LIGO will see. We will see gravitational waves from spinning neutron stars, stars the size of Washington, D.C., made of pure nuclear matter, weighing more than the sun, with little mountains on their surfaces that as the stars spin, those mountains generate continuous gravitational waves, long-lasting gravitational waves. We'll see gravitational waves from black holes tearing neutron stars apart, gravitational waves from neutron stars colliding. We are searching for gravitational waves from the central core engines of supernova explosions. And amazingly, we're searching for gravitational waves and have some hope of finding them from cosmic strings, giant strings that reach across the universe, that are thought to have been created by the inflationary expansion of the fundamental strings that are the building blocks of all matter, that expansion, inflation at the beginning of the universe. Now, LIGO has opened a new window onto the universe, a gravitational wave window, but all of our previous windows through which astronomers have looked are electromagnetic. The astronomers look, for example, with optical telescopes through the optical window, radio telescopes through the radio window, X-ray telescopes on board satellites through the X-ray window. And each time a new window has been opened up, there have been big surprises. The universe seen through optical telescopes was very serene. As seen through radio telescopes and X-ray telescopes, it's tremendously violent. Gravitational waves are so radically different from electromagnetic waves that I think we can be rather sure that we will see big surprises, perhaps even bigger surprises through the gravitational wave windows than we have seen through the new radio and optical radio and X-ray windows. LIGO is just the beginning with gravitational wave astronomy. Over the next decade or two, we will have 4 gravitational wave windows opened onto the universe. There's LIGO looking at gravitational waves with oscillation periods of milliseconds. There will be a window with gravitational waves that oscillate with periods of minutes to hours. There will be a window with gravitational waves that oscillate with periods of years to decades, and a window with billion-year-long oscillations. It is really remarkable that LIGO is such a fantastic beginning. Now I'd like to turn this back to Dr. Franz Cordova, the director of NSF. But I'd like to do so in thanking Dr. Cordova and her predecessors for a fabulous 40-year partnership with, between NSF and the LIGO collaboration. We began with a high-risk dream with very high potential payoff. And we are here today with a great triumph, a whole new way to observe the universe. Dr. Cordova.
Wow. Einstein would be beaming, wouldn't he? This is obviously a very, very special moment. It's a very special moment for me personally to be able to hug a faculty mentor when I was a graduate student at Caltech, and hearing Kip and Virginia Trimble, the spouse of Joseph Weber, inspire students with stories of black holes, which seemed imaginary at the time. And look where we've come now. It's just amazing. So today, you and the hundreds of collaborators who have made this discovery possible mark this day as truly historic. I commend each of you, as well as all the NSF program directors who have stood by you steadfastly for about 40 years. Let's give a big hand to our NSF program directors. Fabulous. You had the vision and the drive, you had the persistence, the commitment to expand what we will learn about our universe over the coming years and decades. As a graduate student at Caltech in the 70s and now as NSF director, I'm struck by how this represents more than just a new generation of observation. It's seeing our universe with new eyes in an entirely new way. I invited Dr. Virginia Trimble to join us today. Virginia is both an astrophysicist and an historian of astronomy. Her late spouse, Dr. Joseph Weber, did pioneering work in the 60s that Kip Thorne already highlighted. And it's really very special that at NSF's LIGO facility in Hanford, Washington, his early instrument is on display. Discoveries of this magnitude do not happen overnight. They aren't made by one person working alone in a lab. They arise from the boldness and brilliance of scientists like Ray Weiss, Kip Thorne, Ron Drever, and Joe Weber at the start. And now, Gabby Gonzalez, Dave Wrightsey, the entire international LIGO collaboration, and so many others whose contributions have led to this moment. And just as one scientist does not do it alone, many times neither can one funding agency or one country. Bruce Allen, the managing director at the Max Planck Institute for Gravitational Physics, is here with us today. Likewise, John Wormsley, the director of the UK Science and Technology Facilities Council, is here, as is Anthony Murfitt from the Australian Research Council. Gentlemen, please stand and be recognized. Thank you so much. I single out these three because the UK, Germany, and Australia have all made direct contributions to the advanced LIGO instrumentation and to the LIGO scientific collaboration. I encourage reporters to talk with them and hear their stories because their role in this international endeavor is significant, and we most definitely could not be here today without their support. Thank you. That said, this is a press conference, and we have reporters here, and also in an overflow room, and listening in via a webcast. Those who aren't in this room will provide questions to NSF staff, who will ask them here in this room. Please, as you ask your questions, give us your name and affiliation, and wait for the microphone. And now let me open this up to your questions, and I'll moderate them and try to determine who goes first. But thank you very much for being with us today. And I saw this one and then you. Here and then over here. Please.
Hello, Davide Castelvecchi from Nature magazine. So, if I understand correctly, this event was spotted even before the actual science run began. Now, is there a sense of, what did you think when you first saw it, and when you communicate it to the public, to the world, is there a sense that maybe this is too good to be true?
I'll start, and I'm sure that everybody here has a comment about that. So, to your first point, it started before the science run officially began. That's actually true. However, we were in an engineering test of our instruments where we were running them as if it were in a science run, and so we were operating them just the same way. We were checking the data the same way. So we were quite confident when this event came in and was vetted that it was a good event. Were we surprised that it was too good to be true? Absolutely. My reaction was, wow. I couldn't believe it.
Yes, I should say that there has been a lot of talk about whether this could have been an injection or a blind injection, and I want to say it's absolutely not an injection. We did check very, very carefully all our injection systems, because in the beginning we thought perhaps one of our tests produced this, but we know it didn't, because we have very careful monitoring systems and we checked all of that. So it was amazing. This was a gift of nature. It was not just black holes, but it was a signal that we could see by eye. Many signals in the future will probably not be this loud, but it was true. It is true.
I'd like to add something to that. I mean, you're getting a good answer, but I'll give you a slightly instrumental answer. And that is, I mean, look, I think it was already said that we saw this at both detectors, both in Louisiana and in Washington State. Now, you have to also know a little about what are at those detectors. We have a bevy of instruments that measure environmental noise, the seismic noise, the possibility that there's that there's a sound, the fact that there could be tilts of the ground, the fact there could be RF interference, everything you can think of. And well, maybe there's some we haven't thought of, but everything we could think of has an instrument that measures it. And what one does is you use those signals and you see if they are in any way coincident with the gravitational wave signal that you suspect. On top of that, there's one further thing. We have, and this is quite elaborate, we have something like 100,000 signals that come out of the instrument. Different things, different servo systems. Everywhere in the system, we are monitoring the interferometer itself. And so consequently, we also look at those channels to see if there's something that is not in the output channel, the proper channel. There are many other channels that could look like the gravitational waves you're seeing in what's called the proper channel. And we didn't see anything. So that's that process that I just described to you is what all of us went through. It took a long time to get this out, and that's part of the reason.
Let me add just one thing.
Yeah.
This signal is just barely not strong enough that it could have been seen in the initial interferometers. And so, after thinking about it, when I first saw it, I was very startled, but then I just realized that if it was just below the level of where you could see it for the initial interferometers, and then you turn on with sensitivity that is 3 times better than that, well, that's what this signal is. It's 3 times above the level where you would have just barely missed it in the initial interferometers. It's because of the big jump in sensitivity from going from the initial interferometers to the advanced interferometers. It's not all that startling in hindsight. It was tremendously startling at the time.
In fact, Kip, it's 10 times better in the region where that signal begins.
And NSF was very pleased and relieved on behalf of all our taxpayers. Great. So we have a question here.
Seth Borenstein, the Associated Press, for Kip or any of the other scientists. Seeing that you saw it so early, first, can you tell us what that might mean in terms of prevalence of gravitational waves, especially at that lower frequency that you can now hear? Does this lead you to believe that there are far more out there now that you're listening with more sensitivity? And in terms of, and I guess the other part of this is, or was this just sort of dumb luck? You got the one every year or a decade, and it just happened to be about the right time you were turning on. And can you explain the importance of these lower frequencies that you can now hear this in that you couldn't before?
Well, let me just say that the technical paper that has just been published during this press conference does contain a very careful statistical analysis that states what this means, what this brings us about information about how often these things may occur. And that analysis does say we ought to see some more over the coming year. And it is very carefully documented as to just what the probabilities of this are. Maybe others can answer in more detail.
Well, my understanding is that the sensitivity can still be tweaked up a little bit too, and that should yield more
So that's the additional factor, is that advanced LIGO is at 1/3 of its ultimate design sensitivity, and over the next few years, that the noise level will be brought down. LIGO will be 3 times better. That means you see 3 times farther into the universe. That means that the volume of the universe you can see goes up by a factor of 3 cubed, or 27. And so after this tweaking of improvement, the rate will be 27, approximately 30 times higher than it is now, and it's already high enough that we should be seeing more in this coming year. So it's really fantastic. We are going to have a huge richness of gravitational wave signals in LIGO.
And that's a promise. All right.
Hi, my name is Andrei Sitov. I'm a Russian reporter with TASS here in Washington, D.C. First of all, gentlemen and ladies and gentlemen, congratulations on the wonderful news, on the wonderful discovery. Second of all, coming from Russia, I obviously have a question about the scientific collaboration with the Russians. I understand that actually the Soviets in 1962 suggested the use of interferometers. Only then they were too expensive to be used. So if you could touch on that a little bit. And most importantly is what lies ahead. What lies ahead? Are you planning, like one of the physicists I spoke to said that the next stage should probably be bringing these things into space without the interference from Earth and trying to measure the effects out there. So what are your plans for the next stage of the research? Thank you.
Let me finish it. Okay, let me try to answer you partly. Look, nobody gave the impression that people hadn't thought of interferometers before. In fact, I don't remember the authors. They were in 62.
Michael Gertzenstein and Vladislav.
Yeah, Gertzenstein was one of them, right.
I know, because I spent a lot of time in the Soviet Union in that era, and they were friends of mine.
And it turns out that it wasn't just with them. But what was done there was not to design a system. It was to look at the concept. Could one measure the existence of a gravitational wave by using light or electromagnetic radiation as a way of detecting them? Then there was actually another effort made in the United States by people at Hughes who built a little instrument that actually a Michelson interferometer was solidly connected to a table, and very much like a readout for a bar. But they also can. What?
It's connected not to a tabletop, but to a large gravestone.
A gravestone. Okay. Well,
this is a historian of astronomy.
Virginia Trimble.
And that came from an idea that Joe Weber had as a way of possibly doing it besides the method that he had chosen. So the concept of this, doing this interferometrically, has been around. It's not, it didn't start right away with LIGO.
Now let me just interrupt you, because I still call Ray the primary inventor, and that is because in 1972, he, having done an extensive analysis, he published a paper in an obscure internal journal of MIT, in which he identified all of the major noise sources that the initial LIGO interferometers would face, and he spelled out how you would deal with each of these and what the resulting sensitivity would be, that you had to have an instrument that was kilometers long for success, but with an instrument of that sort, you should be able to get to the required sensitivities. And that, spelling all of that out in quantitative detail, is what I would regard as really the primary invention of what we see today. But indeed, the outline of the idea began with Gertzenstein and Pustovoit in a Russian journal in 1962.
Let me
talk about the space thing, because we were much involved in that too. That is now, you probably have heard of the project LISA, L-I-S-A, Laser Interferometer space antenna. Many people in the world have been involved, like the United States, the Scots, the Italians, a lot of people are involved in that, and of course the Germans. And what has happened there is actually both good and bad. What's happened is NASA in 2011, this was a very big recommended project by NASA, from the decadal studies. They recommended that this be the third most important thing that they would do. And because of overruns and other problems at NASA, all of that was stopped in 2011. Okay? Stopped to the point where what happens, the Europeans picked it up alone. They tried to push it. They're still now in the process of that. And in just this December, a very successful thing has happened. They have launched something called the LISA Pathfinder, which was a technology test. And so far as I know, one of the more critical things that's happened is that they've been able to release test masses in that system, which was a big worry that people had. Now, the thing is, the compromise that was made in Europe, and I will say something a little bold here, the compromise that was made in Europe to make it so that the Americans didn't have to contribute because they weren't going to, they were going to do a little bit, turns out probably not the best thing to do for the science. The science and the risk involved in doing that space mission. So consequently, many of us are trying to get a collaboration to be reestablished, well, meaningful collaboration between the United States and Europe on this thing. I hope that happens.
Let me just add that the space-based antenna
there are lots of journalists out here that I'm sure would like to ask questions. So go ahead. But you can't answer your question.
Let me just say that will open up the gravitational wave window with periods of minutes to hours. That's
right.
The second of the windows I talked about.
Right. That's very important. Your slide where you showed that they're going to be looking at different phenomena than what we did with LIGO. So that's just key here. It spreads out like the electromagnetic spectrum is spread. This spreads out the gravitational wave spectrum. Yeah. Great. Okay, we have a question here.
Hello there. It's Ivan Semenik from the Globe and Mail newspaper in Canada. Congratulations. First, very briefly, I just hope one of you can clarify the duration of the signal that the detectors picked up. It looks like 0.2 seconds, but I just want to be sure. But more broadly, could you comment and reflect on the sources? Because these are not just any old black holes. They're extremely heavy black holes. And I'm wondering what you think that says about conditions in the universe at the time that these things formed. What might we be learning here?
Yes, I mean these first, the 0.2 seconds is a duration that you see of above the noise, but the analysis that we do is a lot more sophisticated than that. We don't do an analysis by eye, so we can tell We can tell that this waveform, of course, generated long time ago. These black holes were circling each other for billions of years before merging. So we only see the last merger, the last cycles before the merger, and the 1 or 2 cycles after the merger in there. But the signal is a lot longer. You asked about the systems. Yes, these are not heaviest black holes, because we all know about million solar mass black holes in the centers of galaxies, tens of millions. But these stellar mass black holes we knew existed because we know that supernovas exploding and neutron stars colliding form stellar mass black holes, and there is evidence from X-ray observations about stellar mass black holes, but they all had been relatively lower masses, and this is a higher mass. On the other hand, this was a coalescence of 2 black holes, so you don't expect to see electromagnetic counterparts. So you didn't expect to see a system like this with X-ray observations. There might be other things in there, but the fact that these were not seen by X-ray observations didn't mean that these couldn't exist. Now we know they exist, and we will tell how many there are, what kinds of masses there are with future observations. So we have opened a new window. We are not contradicting any theories that there were before.
And let me briefly follow up, because it goes back to a point that's very important. This is our initial run. This is the maiden voyage, if you will, of advanced LIGO. Right? We haven't gotten the detectors to the sensitivities where we expect them to be operating, and in particular at lower frequencies. And there's a relationship between the frequency response of the interferometers and the size or the mass of the signal that we detect. So it is very possible that when we get our interferometers more sensitive at lower frequencies, and that's much harder actually, it's very, very hard to get these things working right at low frequencies. We have our work cut out for us. There may be more massive black holes out there that we haven't seen yet. 100 solar mass. We could be sensitive to 500 solar mass black holes. So there could be a nice discovery space that opens up once we get out there.
So let me add that there are many other scientists from the collaboration here. Vicky Calogera can answer in a lot more detail that kind of question.
Well, and Kip Thorne, I think some of you know, is a consultant on the movie Interstellar. So now we will await Interstellar 2.
You're the executive producer.
We have a question from our webcast or overflow room here.
Yes, we have about 90,000 watching via webcast, and among those is a journalist, Pete Spots from the Christian Science Monitor. He says, what sorts of inner workings can these waveforms probe in addition to providing information on the distance and masses of the progenitors?
In this case of the binary black holes, the waveforms, as I described with this beautiful color movie, they tell us, by comparing those with computer simulations, you infer the wild storm in space-time that occurred. And it is the combination of computer simulations and the observations that are going to get us, in many cases, very, very deep understandings. In this case, when neutron stars collide in the central engines of supernovae. So that's a powerful combination.
Yeah, it's remarkable that those waveforms that Gabby showed reveal so much information about the event. Now, the one thing we should say is we can't speak in certainties here. When we say 1.3 billion years, it's approximately. It could have been further. It could have been 1.6 billion years. It could have been 900 million light years away. The masses could have been bigger, smaller, or heavier, and that's just due to the fact that there's uncertainties in the data itself. But these waveforms give you an immense amount of information about what the sources are, about what the progenitors are, about what the final mass is.
And let me just spend 30 seconds saying that the way we learn this information takes a lot of work. It's not just the numerical relativity simulations. Those are too expensive to do in quantity for search for this signal. It's the analytical waveforms that are matched to those numerical relativity waveforms that we can produce in numbers, and then we can tell not just what's the most likely mass, what's the most likely spin, but also what's the uncertainty in those numbers. And that's why this field takes so many people to work on, because we need to do everything, and we need to do everything right.
Yeah, you brought up a really good point. I think some of our listeners are from our supercomputer centers that we fund, and their contributions have just been seminal in all of this of doing the computational modeling. So a big shout out to them. Let's see, Lisa, you have one more question here, and then we'll take yours in the back of the room.
Okay, yeah. It's actually a question that's been echoed. Speaking of echoes throughout the web, questions about what that means for us here on Earth, and will this bring us further in the science of things like time travel and high-speed traveling?
Oh, Kip, this is tailor-made for you. This is your question.
What's the next movie?
I think it brings us a much deeper understanding, by the combination of the theory and the observation, a much deeper understanding of how warped space-time behaves when it is extremely warped, when it is what we call in the nonlinear regime, and highly dynamical and with very high speeds. I don't think it's going to bring us any closer to being able to do time travel. I wish it would. But that's a different direction, and LIGO is heading in. LIGO's direction is really understanding the wild dynamics of highly warped space-time.
All right, question back here.
Giovanni Caprara from Corriere della Sera in Italy. Which is the role of Italian scientists and the antenna Virgo near Pisa in Italy?
Okay, on Virgo.
Yes. Their role is very, very important not just in the future. We expect the Virgo detector to join the network this year, and then when we detect the future sources, the next detections, we will have a much better localization because we have the Virgo detector working with the LIGO detectors. But it's not only that. LIGO scientists and Virgo scientists have been working with LIGO data and with Virgo data now for many years. So the analysis that we have done and this discovery is jointly done by all the members of the LIGO collaboration and the Virgo collaboration. And that's why we say it took a village. It took a worldwide village to do this.
And I'll add that we are anxiously waiting for Virgo to get online. We have somebody here who's the leader of the Virgo project, or the Virgo detector project, Giovanni Lasordo, so he can talk a lot more about that.
Yeah. Giovanni, wave your hand so people can see who you are. Thank you for being with us. So we have a question here.
Adrian Cho, Science Magazine. So first of all, congratulations on this amazing accomplishment. I'm struck by the fact that, for the first time, humans have detected gravitational radiation. And, this may be a big leap, but, we've just, found the quanta of the three other forces of nature, the weak force, the strong force, and the electromagnetic force. These seem like very classical objects, but it's also incredibly extreme conditions. Does LIGO in this sort of observation have any purchase on moving towards a quantum theory of gravity?
Quantum gravity, yeah. I think the answer is no, but I'm going to, again, there are theorists on this panel.
There is one crucial thing which is highlighted in the paper that has just been published, and that is by looking very carefully comparing the observed gravitational waveform with the results of solving Einstein's equations numerically on a computer to very high precision, comparing those two waveforms, you can see whether or not the waves got slightly distorted in their shape as they traveled 1.3 billion light years. They would have been slightly distorted if the graviton, the fundamental particle that carries the gravitational waves, had a non-zero rest mass. And through these observations, as is described in this paper, LIGO has placed a stronger limit on the rest mass of the graviton than we've ever had before. That limit, I think, check me, I think it translates in more normal language into 10 to the minus 55 grams. I think that's the number. But
know it in kilometers.
You better go look at the
I know it in kilometers also.
Yeah, so
10 to the 16 kilometers.
Pardon?
10 to the 16.
Can I answer you in a different way?
No.
I mean, I'll turn your question a little bit. And that is, I think there's a miracle of sorts here already. Certainly for me there is. I mean, these equations were written in 1915, okay? And they've been tested in the weak fields. I mean, many of the tests in general relativity have been done in the field of the Earth, the field of the Sun, the solar system, and now also in the binary pulsar, which was the Hulse-Taylor object. And these are all the strongest fields that we would have at tiny compared to what we're looking at now. The field has a unity strength, if you want to really say what it is, in this black hole system. And nevertheless, the field equations seem to work, which is sort of amazing to me. This tremendous range of dynamic range of the thing. It's just amazing.
Right. Who has a microphone? Let's get a microphone to some of our... Okay. And then the fellow back here had his hand up next. Okay. Yes.
My name is Makoto Mitsui from the Japanese newspaper, the Yomiuri Shimbun. And also in Japan, gravitational waves detector called Kagura will start observation soon. So could you tell me a little bit what is your expectation of the Japanese gravitational detector?
Right. So,
Can you repeat?
Yeah. So the question
gravitation
came from I'm sorry, I didn't get your name, but a reporter who covered in Japan, asking about, say a little bit about the role of Japan and the role of Kagura, which is the Japanese gravitational wave detector under development right now and under construction right now. So I'll start with just the basics. CAGRA is much like LIGO, much like Virgo. It's a 3-kilometer interferometer, not a 4-kilometer interferometer. It's underground. It's in the Kamioka mines, which has a lot of advantages, actually. They don't suffer from the same kind of environmental perturbations that we do. It's expected to come online probably 2019, maybe 2018. They still have some work to do. It's got some really advanced technology. It's even more advanced than LIGO. They use cryogenics to cool the mirrors to make them more quiet. They don't vibrate as much. All right? That's really pioneering technology. Like Virgo, like the 2 LIGO detectors, all right, CAGRA adds something to this ability for us to be able to localize events. All right? So when you have one detector, this is the best way to say this. Interferometers are like microphones. All right, they're sort of omnidirectional. All right, an interferometer cannot tell you where the event came from in the sky. 2 interferometers gives you a little bit of localization. You saw that in Gabby's presentation. 3 interferometers gives you more localization. It's like triangulating. But it turns out even 3 interferometers doesn't cover the whole sky. It depends on the orientation of the interferometers. In the plane, all right, you can't really see things. So CAGRA, this 4th interferometer that's going to come up in 2018 or 2019, will greatly enhance our capability to localize things. So that banana that Gabby showed you that had, I don't know, 600 or 700 degrees in it, all right, that can shrink down to 10 square degrees, 5 square degrees, making it much easier for telescopes to be able to go and see the events that LIGO, CAGRA, and Virgo are seeing.
All right, we're going to continue questions, but we do have to say goodbye to our listeners on webcast now. Thank you very much for having joined this most important moment.
There, Jeff Brumfield with National Public Radio. So my question is, given you saw this thing even before you started your scientific run, have you seen other